Okay, hello everybody. So you'll remember in single variable calculus, we'd write things like f of x equals x to the third. Then we'd say the derivative is 3x squared. Okay, but this doesn't look linear, and in multivariable calculus we realize that the thing to call the derivative is the linear map. It's the linear map that best approximates our original map near a point. And so we're going to have to choose a point. So for example, if we choose the point x equals 1, well then f of 1 is, 1 to the third is 1 in this case. But f prime of 1, now this thing that didn't look linear becomes a number, 3. And in fact, by the end of this video, we will see that this number, this 3, becomes a linear map, or we use it to make a linear map. And so really, once we plug in at a point, we will get something that becomes a linear map. And so even though in single variable calculus you thought, oh, the derivative doesn't have to be linear, because look, x squared. No. When we plug in at a point, we'll always get something linear when we interpret it the correct way. Okay. So what takes the place of this thing that looks like it's nonlinear, but it's not quite, that we haven't plugged in yet? The answer is something called the Jacobian Matrix. So you can look up the Wikipedia page for this, for example. But here are some examples. I gave 9 examples, all of different dimensions. So over here on the left, what we do is we only have one input variable in each of these 3 different maps. We have one input variable. So all we can do is take the derivative with respect to that variable. And we just do that and record the answers in a column. Okay, this is what people do. It's called the Jacobian Matrix, and they put the derivative in a column. The derivative with respect to one of the variables, in this case there's only one, and they put it in a column. So can you see how these 2 things came from the derivative? Pause and see. Now look at this column, look at these 3 maps. Their inputs are 2-dimensional. So these are 3 different maps with 2-dimensional inputs. And can you see how taking the derivative, let's look at this one first. The derivative with respect to u gives that column. Pause and think about it. Taking partial u gives me that column. Taking partial v gives me this second column. Another way to write this would be, if this was the map f, then df at uv evaluated at the first, so we're moving only in the first dimension, would give me this column. Okay, so these are just 2 different names for the same thing. This one would be d partial v, since v is the second variable. Then if we move in the second dimension, e2, remember e1 in this case would be 1, 0, and e2 would be 0, 1. Why? Because we're thinking about the input space, which is 2-dimensional. Okay. So now think about, can you see how this comes from partial r? Think about that. And when we have r2 to r, this one comes from partial x. This one comes from partial y, the other input. Okay. Now let's look at these ones. Here we have 3 inputs. And so, for example, this third input gives us this column of the Jacobian matrix. How? Well, by taking partial z of these two component functions. So we build the Jacobian matrix by columns. And then, what do we do with it? So first of all, these Jacobian matrices don't look like they're going to become linear maps, because things like x times z squared, that doesn't look linear. But at a point, so let's choose the point, at p equals 1, minus 1, 3. I just chose that randomly. Then what do I get? Well, this is the map f. F of p is, let's see, what is it? 1 squared times minus 1 is minus 1. And 1 times 3 to the third is 27. Okay. And now, what do these three columns become? They become, well, let's see, plug in 2 and a 27. And then x squared 0 becomes 1, 0. And a 0, and then becomes 0. And the last one becomes a 3 times 1 times 9. Okay, again a 27. Interesting. I just made up these maps randomly, so. But now we have actually things that it doesn't worry us anymore. Here are these nonlinear polynomials. Now they're all gone. At a point, when we plug in a point, we get these things. And what are we going to do with it? We are going to create another map. So I'd say a new map. What does it do? Well, let's take a vector. Let's call it, so we're going to move. We're going to move in the input space. So it needs to have 3 components. Let's call them v1, v2, v3. And we'll send it to v1 times the first column plus. We're going to send it to a linear combination of these columns. Our derivative is a linear combination of these columns of the Jacobian matrix. Okay? And so this is a linear map, a new map, linear. Okay? And you see that all these concerning x squared, z to the third, nonlinear things actually don't go into our linear map because we plug in at a point. Okay? And this is how it works in all these situations. So in particular, like, let's say we want to approximate near the point P. We chose this point P, and we'd like to approximate our map a little bit somewhere else. So our input space is 3-dimensional. So we're somewhere in 3-dimensional space. Maybe we are here at P equals 1, minus 1, 3. And let's move a little bit in some vector. And so we're at a new point, and we'd like to know what is f at p after we moved. And the answer is that it's f of p plus the derivative of f at p applied to v. And so what this looks like here, in this case, f of p is negative 127. I think we did that earlier. I'm going to write it as columns. Plus the derivative at p. So I plug in at p, and the Jacobian matrix becomes actual numbers. And then I just take a linear combination. And so this is my approximation formula. V2, 1, 0, and plus V3, 0, 27. So if I actually pick a movement, like if I say I'm just going to move in the direction 0, 1, 1. I'm going to move in that much. What's my approximation? Then I literally put 0 times 227. Okay, well, that's going to be 0. And then what's my second movement vector? A 1 times 1, 0, and a 1. Okay, let's make this more interesting. 2. 2 times 2, 27. And I add these up. I linearly combine them. And I get my approximation for f at this nearby point, a point nearby to my original point P. That point P is where I plug in and I get specific numbers from what? These partial derivatives. This is the partial with respect to the first variable. This column came from the partial with respect to the second variable y. This column came from taking the partial derivative with respect to the third variable z. I plug in at a point and I get a linear map, which I can then use. I use this linear map over here and add it to my output. That, this is sort of a shift. Okay. By the way, just to be clear, the output space is two-dimensional. So I'm mapping all of three-dimensional space over to a two-dimensional plane. This is sort of a new thing that we haven't seen. It's hard to visualize how three-dimensional space would squash down onto a two-dimensional plane, but it can. Here's a formula that does it, and does it non-linearly. And here's a formula that does it linearly. Well, here is linearly sending R3 to R2. And in general, this is how it looks for all the different cases. If we're going from R2 to R3, then we're going to look like this. So our input variables, if we move a little bit, those will be the v's, and that will be the numbers that we use in our linear combination. And if we've chosen a point, all these, these dots here that I didn't write anything, those are supposed to be actual numbers, right? Because we've plugged in at a point P. So we've changed the outcomes of these partial derivatives. Plugging it at a point gives us actual numbers. We take those columns and we use them to linearly combine. And this is actually the definition of matrix vector multiplication. So we have this matrix, and we have, in this case, the input space was three-dimensional, so we're going to move in our input space. And this matrix vector multiplication is defined so that it's a linear map. That is the reason for that definition. Okay, so hopefully this was helpful. Then you see that, take a moment to look at all these approximation formulas. They're just sort of showing you the different shapes that these things can have. So here we have our maps with a one-dimensional input and outputs 1, 2, and 3-dimensional. So there you see there's always a one-dimensional input, so our movement vector is just a single number. Our input space looks like that. We pick a point P, and then our movement vector is some number, like here, maybe it's -3. V1 equals -3. And so we just put a -3 there. And since we've chosen a point P, we'd plug in, and all these would be numbers. What were they before? They were these things. These, this. All those things that they worry us, they look like they're nonlinear. When we plug in, they just become the numbers, and that is the vector we use to linear approximate. In the picture, we're mapping R to, let's say we're mapping to R3, and we have some curve, and here's f of p, and then we're going to move. And that movement is that vector. And how much is what was our movement vector? V1. Okay. So, pause this video and see if you can do the same computations. See if you can match up these dimensions with these, and these dimensions with these three here. And hopefully this was helpful. So, there's one more thing. I said that we would discover how this becomes a linear map. So let's discover it. So in single variable calculus, we would have drawn the graph of this map. Let's give me some more room. So maybe it looks like this. Okay, and at the input, I chose the input 1. So there's 1. Had the output 1. Okay, and then at the input 1, I plug in, and my nonlinear thing becomes a number, so that's a 3. Now, what does that 3 mean? What it means is if I step 1 unit to the right, I'm over at 2 now, but this was a step of 1, so I'm going to call this v equals 1. It's an input movement vector. What should my output be? How should my output change? My output was at height 1, and now the claim is that it should move 3. 2, 2, 3. It moved 3 units up to the height 4. And what is that? Well, that is exactly what we would get if we chose the tangent line to this graph. It had slope 3. Slope 3. And so a change in the input produces a change in the output, and it's a linear change because, for example, if I double my change and I move v equals 2, so I did, instead of v equals 1, I doubled it, then my output change should also double. It should move now 6. It shouldn't move 3, it should move 6. So now, I started at 1, I moved 6, so I'm all the way up at 7. Okay. And this is what you get if you use the approximation formulas, like f of x plus v is approximately equal to f of x plus the derivative of f at x in v. In single variable calculus, we would have said f prime of x times v. And then we would get, 1 was our output, f of 1 was 1, plus 3 was our derivative, f prime of 1 was 3. When we plug in at the point 1, we get 3. And v is our movement. So if we move v equals 2, we get a 6 here, and we get 7, and that is where we are. And so really, what we used to call the derivative, we just need to plug in at a point, and now it becomes something that will be used in a linear map. What is the linear map? It sends the number v to 3 times v. This is a linear map from R to R. Okay, exactly the same way, all these Jacobian matrices that are partial derivatives with respect to the 3 input variables, we plug in at a point and we get 3 actual vectors, 1, 2, 3, that we will linearly combine. And that is our linear map, this time from R3 to R2. Okay. Hopefully that was helpful.